So the recording is now started. So I hope everyone can see my screen. We're taking a look at a fluorescent image with 5 different stains down here, or dyes should I say, and with any fluorescent image in Halo, you can toggle all of these off and on using the tick here, and you can actually collapse this channel box as well. Just one thing to mention is we do have a graph here, so you can come in and adjust the view settings if you wish, using these sliders like so. That's not going to change any of the intensity values which are generated, so it won't change any of your results. It's just simply to improve your view settings if you need to for your fluorescent image. So when we first want to load up some new settings, just as a reminder, if we come to setting actions and then load, you've got a list now of all of the algorithms that you'll have access to. So I have access to all of the algorithms, and as a new kind of feature of 3.1, we now only show the latest version of the modules within this box here. So by default, you'll be pushed towards the newest release, which has small improvements and changes, and that's what we'd recommend using. If you do want to use any previous versions, if you just tick show all installed modules, then you'll have access to earlier versions, for example here, version 3.1. But just to recap, we do recommend using the module that has the highest number. So the module today we'll be looking at is Hyperlex FL, and this is version 3.2.1, and this was released probably only maybe 2 weeks ago, 1.5 weeks ago now, so this is a relatively new update to this module. And we'll go through all of these parameters here, and I imagine as you guys have been to the previous sessions, a lot of these settings, particularly the nuclear optimization parameters, will be very familiar to you. But the first one we've got here is our analysis magnification, and if we expand this panel, we'll see you've got image zoom, and that's currently set at 1. And that means our analysis algorithm will run at 1 times the maximum magnification for the image. And in this case, it's 20 times, which typically works very well. If you maybe scanned at 40 times, then you could bring this image zoom down to 0.5 to run your algorithm at 20 times, just to speed up a little bit. If you were doing ish or fish, again, just as a reminder from the last session, we do recommend scanning at that 40 times. So we'll leave this as 1 for now and move on down to dye selection. And one of the new features of this module is the option to autofill our dyes, which is a really nice way to speed up the workflow. I mean, I only have 5 dyes here, but when you're doing the super multiplex staining, maybe you have 30 dyes, even more possibly, you can just simply press autofill. Halo will ask you whether you're sure. You can press yes, and then it's very fast as we only had 5 dyes, but the table has now been populated and you can see these listed below as well. If you don't want to quantify all of your dyes, then you can go ahead and just press remove. That's quite nice and simple as well. So we have those additional options. Then below we've got number of phenotypes, and again this is present in almost all of our modules now, so you can type in any number that you wish, and then again the table will populate at the bottom, and then for this example we're going to have a look at creating 3 different phenotypes, and what's great about the phenotypes is that they will be, you can name them and they'll be shown within your analysis results. And then we can go on to use those phenotypes for spatial analysis, again just saving time without needing to create complex filters in our data set. We then move down to our nuclear detection settings, and so these parameters will be very similar, if not identical, maybe slightly different order to what we looked at with multiplex last week. So we'll take a quick run through of these, but just as a reminder, if you are new to Halo, as you guys will be, you'll have a very small message down the bottom just to give you a little bit of an explanation as to what each of these parameters are. And again, within the user guide, towards the bottom, you have some information on the input parameters, which are all of these parameters. So maybe for 4 or 5 sentences for each one. So you can really familiarize yourself with what each of those mean if you're unsure. So one thing to just point out before we put on our real-time tuning window is down below you have the option here to select the nuclear die, and the nuclear die by default will just be the first stain. So if your first stain isn't DAPI as it is here, then you can just go ahead and change this via the drop down. And if perhaps you did have other nuclear dyes which you wanted to incorporate here, then you can adjust the number as well. Typically with fluorescent images we don't need to do that, so we'll go ahead and leave our number of nuclear dyes at 1, the dye selected as DAPI, and then that will obviously contribute to 100%, which is equal to 1 here for our nuclear detection. So I'll pop on our real-time tuning window, and then we'll work through the parameters at the top here in order to improve the detection, what we're seeing here. And what I personally like to do is toggle off all of these channels here. So we're just left with our DAPI channel or our nuclear channel. And then just as a reminder, you've got the option to toggle that transparency within the real-time tuning window, and also, toggle the markup off and on, and then also adjust the transparency as well, so we can see what we're identifying, kind of taking a first pass at how the unoptimized settings are working. So what I have first noticed is perhaps we're picking up some background within our nuclear detection markup here. So the first parameter I'm going to go to is our minimum nuclear intensity, and I'm going to look to increase that in order to try and remove this background here. And I do quite like to use the arrow keys on the keyboard just to have a little bit more control. Of course, if you're wanting to increase this a lot, then you can use the slider to speed that up. Then again, I'll toggle off and on and take a look at what's being detected. And of course, it's a good idea to move around your image and make sure you've not kind of increased that minimum nuclear intensity too high before moving to a different area. The parameter below is the maximum image brightness, and this is also a new parameter for our HyPlex module. And you can see we've got a little description here, but if you've got very dim fluorescent images, so your working range would be towards the left-hand side of this histogram here, then you can bring that maximum image brightness down just to basically increase your working range within these parameters here. And one good way to possibly tell if you need to bring that maximum image brightness down is to just adjust the nuclear contrast threshold with the keys. So we're going up or down by 0.001. And you can see in my real-time tuning window, I'm having small changes visible, which means my maximum image brightness is fine. The parameters are responsive. If you're kind of going up by 0.5 or even 0.1 and you're not seeing much change within that real-time tuning window, then perhaps you need to look at possibly adjusting this maximum image brightness here. The parameter below is our nuclear segmentation aggressiveness, so we can increase or decrease this in order to segment any interconnected nuclei. And you'll see as I begin to increase this, we have some divisions appear between our nuclei, and of course you can toggle off and on using this real-time tuning window. If perhaps your segmentation aggressiveness, if you pop it all the way up and it's not looking to effectively segment any interconnected nuclei, this is where I would perhaps recommend coming back up to your contrast threshold, so you can also increase this very slightly to further segment your nuclei. So you see maybe here, for example, if we bring that back down, it's joined back up as 1, and then we can increase to segment. Now I'm not entirely sure if we are wanting to segment, so maybe we'll toggle off and no, it's probably meant to be 1 nuclei, but that's just an example of how contrast threshold can be used. We then have the option to fill nuclear holes. So if we pop this to true, you see, for example, here, this nuclei has been divided into 2 ordinarily with this parameter set to false, and we can swap that to true, and you'll see it's now joined up as 1 nuclei. So this fill nuclear holes parameter can really help, perhaps if your nuclear staining isn't quite even. So we can see here, maybe if I increase the change the view settings slightly, you'll be able to see better. The staining within the nucleus is maybe slightly lighter in the center, so Halo is trying to over-segment those cells. So by swapping the fill nuclear holes to true, we're able to bring that back down. The other option here would maybe be to try and reduce that segmentation aggressiveness, which also pops our nucleus back together, or again bring that nuclear contrast threshold down, which might here also aid in the over-segmentation. So all of the parameters tend to be interconnected, so you can change a few different ones, so you can really optimize the detection across the whole image. We then have our nucleus size, so this is our minimum and our maximum. So again, you've got the sliders which you can adjust, or my personal preference is to just simply go in and type in a value, for example. Sometimes you might need to bring down the minimum here to put up the very, very small nuclei, so feel free to adjust those as needed. We then have our minimum nuclear roundness, so we can increase this to eliminate nuclei which are not perfectly round. So you can see here we've got some elongated shapes, which we can look to eliminate from the analysis by bringing up that minimum nuclear roundness value. That would obviously be up to you as to whether you'd like to exclude those or whether you are happy to include them within your analysis. So we'll then move on to our membrane and cytoplasm detection. So we've got some parameters here. So the first one is maximum cytoplasm radius. And if you are wanting to detect markers in the cytoplasm, then we will need to add on a cytoplasm radius. So if we just type in 2, for example, you'll see now we've got a white ring which has been essentially drawn around the shape of the nuclei, so that's just dilated out, and this is our cytoplasm compartment. If we pan across over here to our sort of more complex looking nuclei, these guys actually have a membrane stain. This maybe is looking sort of a bit higgledy-piggledy. So we can actually use our membrane stain in order to help segment cells as well. If that's the case, initially you've got this membrane segmentation aggressiveness parameter, and this will have no effect on the markup until we plug in a membrane stain. So the first thing we need to do is tell Halo the number of membrane dyes. So we can just type in 1, for example, and then we have a drop down available now, so we can go in and select the dye that we would like to use to segment based on membrane staining. And hopefully you should have seen that the markup within this real-time tuning window changed when we moved on to segmenting based on the membrane. So perhaps multiple cells are being joined up as 1. Whereas when we will be segmenting based on that membrane, we'll now have different sort of segmentation, which is definitely improved in this instance. So we'll then move on to setting our thresholds. So DAPI is our only nuclear channel here, so all of our cells will be positive for DAPI if there's a nucleus present. But what we can do is choose to threshold based on these. And again, this is a new addition to our HyPlex module, we've now got the three sliders, which we also see in cytonuclear and cytonuclear FL. So we're able to set the threshold for weak, moderate and strong staining, and also generate H scores based on these sliders. So if we look to bring the first slider down here, so this is just for our overall positivity, you'll see in the real-time tuning window our nuclei turn blue, which means they are positive for our DAPI stain. Now, if we bring down the other slider, we don't actually see any changes in the real-time tuning window, so everything's still blue. So we don't know what cells will then be moderately positive for a particular marker. So if we come down to the output image and choose our channel of interest, we can now see so all of our cells, all of our nuclei are moderately positive. So we can go ahead and adjust that slider like so, and then all of these staining intensities will be reflected within the real-time tuning window. I guess DAPI probably wasn't the best example to use for this, as you're probably just looking for positivity or negativity, so we can always put the sliders back to the top. And if we have the sliders back at the top and we're only interested in looking at overall positivity, then Halo is now clever enough to eliminate either of these moderate positive and strong positive elements from the results. And I'll mention this once we do generate some results shortly, but we won't have unnecessary and unwanted columns and rows of data. All of that will automatically be eliminated for us. So I'll pop that back to co-localization now. I don't need to look at DAPI in the cytoplasm or the membrane, so I'll leave all of those parameters alone and move on to our next dye. And this is our FITC channel, so perhaps we can turn this on and then move over to an area with some positivity. And this looks to be cytoplasmic stain. So if I come to my cytoplasm thresholds and begin to slide this down, what we should see is different cells turning positive for this particular marker. And again, we can toggle off and on and make sure what we're seeing is representative. So the real-time tuning window represents what's positive within the biological image. But you might think, oh, I'm just sliding up and down sliders there. I don't think that's particularly accurate. So one option you do have is if we come down to the advanced parameters here and set our object data to true, what we can do is run a quick field of view without any of our intensity values set in order to generate that cell data where we can look at the intensity values for each of our cells. And this will give us a numerical value to kind of base the thresholding off. So if we hop across to results here and maybe scroll across and toggle off our markup and then maybe just have our FITC channel on. So if we think, yep, this is a positive cell, we can then take a look at the intensity value, which is 40.32. This cell is negative, and that's down at 7.27. And then this will give you kind of a value as to what's positive, rather than just simply sliding the sliders up and down and seeing what's in the real-time tuning window. Although that's great to show you you're on the right track. This might just give you a little bit more guidance. So you can take a look then at each of the values for your other channels as well, maybe make a note of them and set those thresholds a bit more accurately. So we'll come back to our analysis tab, pop on that real-time tuning window, and now perhaps I'd like to type in a value of 30 based on the numerical value from the results table. And you'll see now I've got my positive cells in the cytoplasm compartment are visible. So that's the only compartment I'm interested in here, and I don't want to generate the results for weak, moderate and strong. I just want to look at overall positivity. So again, I'll move down to the next dye. So the next one is Cy3. And again, this may be looks to be cytoplasmic and perhaps nuclear. So we can come across to our nuclear compartment, and again, adjust that slider. We could use the values from the other channel. And we want to maybe look at in the cytoplasm as well, so we can bring those sliders down. But as with green and yellow, it's quite difficult to tell when a cell is maybe dual positive for a marker, so you might not know whether you set that threshold effectively. So what I would recommend when you're setting the thresholds for individual channels is to change that co-localization markup to the channel of interest, and then it's a little bit more clear within that real-time tuning window. And again, we can toggle off and on, make sure we're picking up all of those positive cells. So carry on and set the thresholds for our other compartments. Again, if you have set your output image to a particular stain, just make sure you swap before you go ahead and set those thresholds, else the changes won't be reflected in the real-time tuning window. So I'll just set these nice and quickly. Excellent. So within each of these stains here, we have exactly the same parameters. So we've got our parameters to set the threshold in the nucleus, the cytoplasm, and the membrane. And now below each of these thresholds here, we have a completeness threshold. So what this can do is if maybe you have two nuclei which are close together and maybe the stains are overlapping, but really that should not be the case and Halo is detecting them as false positives perhaps, you can go ahead and set this nucleus or cytoplasm or membrane completeness threshold in order to eliminate that false positivity, which could be perhaps be generating phenotypes which are not biologically possible. So maybe we'll take a look at this with our FITSI channel. So if we pop on just the FITSI here, try and find some examples, can be tricky. Maybe if I bring the threshold down a little bit. So we've got lots of positives here, and hopefully if we change this, we might be able to see an example in the real-time tuning window. So if we increase this percentage completeness threshold, what we're telling Halo is that a minimum of this percentage, so 58.2 in this case, of this particular compartment must meet that minimum threshold value. So if we bring this down, you'll see maybe over here, this cell doesn't look to be positive for our cytoplasmic FITC marker, but it is coming up as positive here with our particular positive threshold value of 10. So we can increase that percentage completeness threshold in order to eliminate cells like this, which are being detected as false positive when they're not actually. So that's a really nice way, particularly if you're working with maybe immune populations which are clustered together and the staining might be a little bit blurred and bleeding over into the cytoplasm of another, to really eliminate those from your analysis. So we'll then move on to setting our phenotypes here. So I'll just go ahead and pop the output image back to co-localization. And we'll move down to our first phenotype. So in this example, We're not typically sure what each of these markers are looking for, so when we have images given to us, we're just given kind of the channel name, so we can make up phenotypes as we wish, really. And in this example, we're going to try and generate some phenotypes for CD4 positive and then CD8 positive cells, and also tumour cells. And then we can go ahead and use those within our spatial analysis element. So the first thing we'll go ahead and do is type in the name of our phenotype. So for example, CD4 positive. And then the next step is to set the number of criteria. So again, you've got the sliders here to increase the number of your criteria, or you can just simply go ahead and type in a value that you require. We then have the option to set the channel and then the filter logic in order to go ahead and specify those phenotypes of interest. So in this example, maybe we could have the FITC channel as positive, and then our second criteria could be the Cy3 channel needs to be perhaps negative. And if we come down to the output image, you'll see now phenotype 1 has been renamed, and we can actually turn on our real-time tuning window to identify those phenotypes of interest. Maybe our second phenotype could be CD8 positive, and again we can set the number of criteria here, exactly the same steps. So maybe for this example it could be Cy3 positive and maybe FITC negative, so the opposite. And again we can take a look to see if we've got any of those cell types of interest. And then finally we could have our tumour cells, and maybe these only have one criteria, to be positive for our membrane stain. And the last thing to mention within the phenotypes is if you have been changing the output image to your phenotype of interest or the channel of interest, make sure you pop it back to co-localization before running your analysis. So we could then move down to the advanced settings. So we've got the option to store object in brackets cell data, and this was set to true, so we could run our small field of view analysis to take a look at those intensity values. And if you are going to be doing spatial analysis, then you do need to set this parameter to true. If you're not and you're just happy to have the summary data, then you can also go ahead and set that back to false. So in this instance, we'll leave this as true. And we also have the option to apply a classifier here, which we'll go ahead and do so we can take a look at the summary results which are generated with a classifier. I'll just use a pre-saved one. And then I'll go ahead and specify the class list. So these are the classes we would like to have our analysis ran within, which in my case will be the tumour and the stroma compartments. And by selecting these classes, the summary results will be divided into the tumour and stroma compartments, so we can go ahead and really take a look at the differences between our two class types. We have a classify registered option, and that's something we'll cover shortly when we move on to the registration portion of the training. So I'll go ahead and zoom out a little bit, and we'll just do a local analysis of the field of view. Actually, no, we'll save these and we'll do batch analysis to show you how that works. So we'll call this 6plex classifier. Press save. So I've saved those settings via setting actions and save. And now to launch batch analysis, if we go to the studies tab here, we can select our image or multiple images if we wish. Right click and come down to analyze, and you'll see we've got the option to choose from analysis settings or classifier settings. So because our classifier has been embedded and saved within our analysis settings, by selecting this here, which is what we just saved, Halo will first run the classifier and then it'll run the HiPlex analysis. So we don't need to try and select classifier and run that and then the analysis and run that. It'll all be completed within one analysis job essentially. I'm just going to check what annotation layer my yellow one is to speed up the analysis. So it's labelled as whole tissue, which is helpful. So the reason I'm analysing the annotation layer is we've got plenty of black space around our tissue. So analysing our annotation layer will just kind of focus the analysis within the region of interest and save time. So I'll go ahead and press Analyse, and so this job and any other jobs which we had perhaps selected to analyse with the same settings will go off to the processing node, and if we did have multiple, they would be listed here. And it's just going to take a few seconds for the analysis to kick in. So firstly, the thing which will run is the classifier, and then once the classifier has run, the Hyperplex analysis will then run on the image as well. And this should only take a minute or two. If you are running images or analysis in batch mode, you will need to close and reopen the image in order for the analysis markup to appear. I guess while we're waiting, I can ask if anyone has any questions in the meantime.
Hi, Natasha. Thanks for that nice presentation. I would like to ask if I want to process a batch of images, but I want to analyze only different annotation layer in each of these images. Like they vary in position in the XY axis. So what would be the easiest way to do it?
When you want to launch analysis on different annotation layers from different images, so these images both have different annotations, it's the exact same step. So you'd select those images, come to Analyze, and then if you choose Annotation Layer in brackets S, then you can choose a selection here. So rather than all, you can choose which particular annotation layers you'd like to analyze across both of those images. So all of the annotations across the images will be listed here. And then you just go ahead and press Analyze, and that will go off to the processing node and be run in batch mode for each of those annotation layers. Perhaps I was slightly optimistic with this whole slide image, but we're nearly there. Another thing that I can mention whilst we're just waiting for hopefully just a little bit longer for this analysis to be done is any analysis results which you run, or any analysis which you run on your image which generates a set of analysis results, will be visible by this drop down here. So you can see I ran an analysis earlier on today across the whole tissue. We then just ran that small field of view, and then once our analysis of the classifier has been ran, that will also be available in this drop down here. So we can click onto those different sets of results in order to pull them up and take a look at the data. Fantastic. So we're finally completed. So I'll shut down the image and open it back up again. And if we hop across to our results here, so you'll see initially we've got our summary results up here. And because this is a whole slide image, it can just take a second or two for our individual cell data to populate the table, which it's now done. So as a reminder, we ran a classifier across this image, which I'd previously generated and saved. And if you want to toggle between your cell-based markup and your classifier markup, you can press Ctrl and E, which is a nice shortcut to toggle between the two. Or if you hover over the markup you can select from the drop down here. You've got the toggle action, so you can toggle between the classifier markup and the analysis markup. But obviously that shortcut is a little bit quicker. So we've got our summary data up here. So we've got the classified area broken down into the different compartments, our tumour and our stroma. We then have our total cell counts, DAPI positive, FITC positive, Cy3, Texas red and Cy5 positive. They're just our total cell counts there. And then this is broken down into our compartments. So what you can hopefully see is that we're just focusing in on DAPI and Cy3 within the nucleus. And we don't have very, very low readings for the nuclear compartments for the other channels. So they have automatically been suppressed. We've then got some readouts for our cytoplasm and then for our membrane. And then we've also got our phenotypes here as well. So our CD4, CD8 and tumour cell phenotypes. We have our counts generated for those cells. And then all of those numerical values are given as percentages just here before we're given average intensity values for the different compartments and overall. We then have some general sort of cell statistics, so average cell area, nuclear roundness, that you can take away if you wish. And then below we now have all of those values given across our tumour cell, a tumour class. And if we scroll further down, we have the exact same readouts for our stroma compartment as well. So you can really take a look at the differences between those compartments when you apply a classifier within your analysis results. So if we move on down to our data table here, so this is all of our individual cell data, and if we click on an individual cell, then the corresponding row of data is highlighted, and the same if we click on a row of data, then the corresponding cell is highlighted. So hopefully you can see that small white box on the image. So this is all of our cell data here. So we've got all of our readouts for every individual cell. So the intensity values within the various compartments and for the various stains for each of these. And again, just restricted to the compartments that we're interested in. You have the cell area, it's the same cell statistics here. And then you've also got a classifier label here. So the options will be stroma or tumour for our different class types here. So you can also filter this data based on whether the cell's in the tumour or stroma compartment as well. So now we've generated our cell data, what we can go ahead and do is some spatial analysis. Now the first thing we want to do when we're doing spatial analysis is apply a filter to any of our columns, and then we can go ahead and plot that data in a spatial plot. And I did just very briefly show you how to filter based on the classifier class, so whether it's tumour or stroma, and hopefully you saw that we had a very small sort of filter icon here. So you can click on this, and when you're looking at phenotypes, as we are here, the option is 0 or 1, so 0 is negative for that phenotype, 1 is positive for that phenotype. So for example, we want to plot our CD4 positive cells, we can go ahead and select 1, and then we have our CD4 positive cells are now listed within this column here. And if we come to Object Actions and Plot and Spatial Plot, we've got the option now to give a name to this point series. So this will be our CD4 positive, and we can press OK. And then very shortly we'll have a spatial plot showing each of our CD4 positive cells across the whole piece of tissue. If we want to add other pieces of data to this particular image, then what we can do is come to the bottom left here and close down that filter. So now our data table has all of our different cells, and we can just simply apply another filter. Leave the spatial plot open and do the exact same steps. So object actions, plot, spatial plot, and give this a name. Wait a second or two. And then we have our CD8 positive and our CD4 positive cells plotted onto the image. So if you want to change any of the colours of the of each of these dots here, you've got your plot layers over here on the left-hand side. So if you right-click and go to Properties, then here you've got the option to go ahead and change the colour, change the symbol, change the size. And if you are wanting to overlay any spatial analysis on top of your biological image, which is something we'll look at shortly, you won't be able to change the colour once that markup's generated, so it's important to do it before running any spatial analysis. And from past experience, I typically find that the 3 pixels for this particular image might be a little bit small, so I might want to increase those just to make it easier to see. And then we've also got the option here to go ahead and select a colour. So maybe I'll go for, we already have red on the image, I'll go for aqua and press OK. And that's been changed on our spatial plot. And we could do the same for our CD8 positives as well. So we could increase that size and then also change the colour and the shape if we wished. One other thing to note is whilst we're here within the properties, you've got the option to pull up a colour spectrum here. And what we can do here is take a look at any of the outputs which were generated. So if we maybe look at DAPI nucleus intensity, press apply. What we can see here with our squares, we toggle off our CD4 markup, is we've now kind of got a colour spectrum. So we've got cells which have a very high DAPI nuclear intensity in red, and then cells which have a lower one in the blue colours. So you can do this for any of your markers, and it's quite a nice way to display those various intensities. So I'll just go ahead and take that back off again. And we've now just got our CD4 positive and our CD8 positive cells in a spatial plot ready to perform our spatial analysis. So rather than being in the analysis tab, our spatial analysis is tucked away here. So once we've made that spatial plot, we can come in and perform a spatial analysis. And if you are wanting to run spatial analysis in batch mode, then you will need to run through this at least once. So plotting the data, generating your spatial analysis settings and saving them before you're ready to go ahead and do that batch analysis. So we've got 4 different types of spatial analysis. So we've got nearest neighbour, proximity, infiltration, and density heat map. So the first one we'll take a look at is our nearest neighbour analysis. So this is very simple. So we're simply finding the nearest cell type to every other cell type essentially. And in this case, we've just got our CD4 positive and our CD8 positive cells. So we can go ahead and plug those in here. And we've also got the option to store object or pair data. So we'll go ahead and press true. And we've also got the option to generate a markup image. So we'll be generating a spatial analysis markup on top of our biological image, in a similar manner to how our cell-based analysis markup is displayed. So I'll just press analyze. This might take a second or two across the whole image. But just one thing to note is that setting store object data and generating markup image to true, you have a message here on the right hand side which says it's going to increase how long it takes to run for both of these, and also if you're generating more data, it's also going to take up more space within the database. So that's just something to bear in mind if you're not going to be using that pair data or particularly interested in taking a look at that overlay, then it's best to leave those to false. So what you can see now is we've got a nearest neighbour line series visible on our image. So this is in the grey, and we can go ahead and change the colour of this again via the properties if we so wish. And then we can zoom in and we can see those changes applied to our plot. So we've got our CD4 positive cells at the centre here, and then we're branching out to those CD8 positive cells. Now, if we zoom in and take a look at our biological image, hopefully you guys can see, we've got our CD4 positive cells, and then we've got our CD8 positive cells and the nearest neighbour line series. So within this analysis, we've got 82,103 CD8 positive cells in the pink here, and then the average distance to a CD4 positive cell, so to the blue cell here, is 50.38 microns. And then we also have the number of unique CD4 positives, which is almost 18,000. And what that value means is, if, for example, we have multiple CD8 cells all connecting to a CD4, a single CD4 cell, which is all of their nearest neighbour, this cell here will only be counted once in this output here to kind of give you almost a ratio between the two different populations. We then also have our cell-based pair cell-based data here. So we can click on any of these pieces of information and have the pair highlighted. So here, for example, we've clicked on this row, and then we've got the corresponding pair highlighted with a square box. And you've also got the distance for that particular pair, as well as the ID and the XY coordinates. So nearest neighbour is a very simple analysis to run. So we have nice simple outputs here. So the next one we'll take a look at is the proximity analysis, which also gives you this average distance as well as a little bit more information as well. So I'll pull up my plot again. And because we've already got these two plot layers added, we can simply go ahead and perform another spatial analysis. We don't need to run through replotting all of this data again. So select proximity analysis, and you'll see here we've got similar drop downs, so we can measure a certain cell type of interest. So maybe if we want to look at CD4 cells within a set distance to CD8 cells, and you're free to go ahead and adjust this distance as you see fit. So maybe we'll leave it at 100. And then we can also adjust the number of bands, and the number of bands is how this distance is divided up. So if we, for example, change this to 10, we'll be looking in 10 micron increments within this 100 micron distance, and that will be reflected within the summary results and also a histogram, which will automatically be generated. So we'll leave object data and the markup image off for now. We'll just go ahead and press analyze and take a look at what results are generated just from the basic proximity analysis. So our proximity analysis has been completed. So if I toggle off other plot layers over here, what we can see now is you've got CD4 positive cells which are within the 100 micron distance, and they are in blue, so the majority of cells are within that distance. And then we've also got CD4 positive cells which are outside of that 100 micron distance, and then they are in yellow up here. If we minimize that spatial plot, we've now got our summary data here. So we've got our counts for our different phenotypes, the counts of CD4 positive cells that are actually within that set distance. We have that given as a percentage, so 97.3%. We also have the average distance and then the number of unique CD8 positive cells, which is the same readout as what we saw in the previous analysis with nearest neighbour. The average number of CD4 positive cells within that 100 micron radius of CD8 positive cells, which is almost 2.5. And then we have the total count, so the 40,621, and that's broken down into the 10 micron increments throughout the 100 micron distance. So you can see we have that, have those counts broken down here. If we left it at 20 bands, for example, we'd be looking at 5 micron increments. So you can decide the number of bands you'd like to divide your distance up into. And I mentioned that would be reflected in the histogram. So you can see here we've got 10 different bands on the graph. And we also have the option to change the title of the histogram and also the subtitle if we wish. And we can also save this or take a snapshot, and then that snapshot can be used outside of Halo and applied elsewhere. So I'm going to come back to the plot here, and I'm just going to firstly go to the density heat map before moving on to the infiltration analysis, as I want to replot some data for the infiltration. So if we come to density heat map, this is the newest spatial analysis which was added when we released Halo 3.0. And what we can do here is take a look in a set radius. Sorry, if I go back a step. So what we'll do is we'll pick a cell type of interest. So we could do CD4 positive, CD8. And as being as now, we've done another proximity analysis where we've got other plot layers which have been added. We could also then do density heat maps or nearest neighbor or infiltration analyses with these other data series as well. So you can build up your spatial analyses as you go. But what we'll do is we'll select a cell type of interest. And what we'll do with the density heat map analysis is we'll look in a set radius around every cell, which is positive for our phenotype of interest. So in this case, we'll be looking in a 25 micron radius around CD8 positive cells for other CD8 positive cells. So we're looking at the density of a cell type of interest, and that will be across the whole slide in this case, but it can be restricted to a field of view or an annotation layer if you so wish. And what we'll be able to see is the density of this phenotype across the whole tissue. So we can look at hotspots and where these cells are localized or where clusters of these cells are localized across the tissue. So you can adjust this radius. You don't have to leave it at 25. You can change it to 50, 100, whatever your preference is. I guess that depends on the size of the cells. And you can also change the heat map colors as well. So I've just double clicked. And we've got, for example, TMA, so just red, yellow and green. And we've also got alternate colours as well. But we'll leave it at probability for now. And we have the option to scale to image. And we also have the option to customize that scale as well. So if perhaps we were running a density heat map in batch across multiple images, we might want to customize that scale just so the heat map colors are equal across each of our images which we choose to analyze. Therefore, you can take a look and you know that if a hotspot or an area is red on one image, then obviously it means a similar density is also visible in another image. Whereas if you just choose scale to image, then you might be taking a look at different visual representations. So that's just a point to make there. So if we just select scale to image for now, we'll let this density heat map analysis run, and then we'll take a look at the results which are generated. So our analysis is complete, not quite as spectacular as I was hoping for, but what we can see here is a heat map essentially. So areas which are red are our hotspots or our higher density, and then areas which are blue are areas of lower density. And of course you can toggle that transparency markup off and on, and you could also make a figure using this example markup. Over here on the left hand side, got area analysed, got the counts for CD8 cells, which is what we were interested in looking at. The average count within that 50 micron radius, average densities, and then you also have minimum values as well. So those dark blue areas, which are the lowest density, will have no CD8 positives within that 50 micron radius, and then areas of the highest density, so our red hotspots, have up to 103 CD8 positives within that 50 micron radius. So these are some nice simple outputs, and it can be a really impressive visual display, depending on your, obviously, distribution and density, and what you're looking for. So the last thing to do for spatial analysis is our infiltration analysis. And now the reason I left this to last is because we need annotations for this particular analysis. And what I prefer to do is draw my annotations within the annotation tab here. So here, for example, I've got my tumor, which is maybe my invasive margin or tumor border. So that's been drawn in red. And then I've also got the maybe ROI for the analysis, so the region of interest. This, of course, could be a whole slide, but you do need that region of interest in order to fill in the different options for the infiltration analysis here. So you do need that tissue annotation layer, which would be the ROI or the whole slide, if you so wished, but you do need that to define where your infiltration analysis is going to take place. So if you don't want to spend ages drawing around your tumor margin, what you can do, just as a reminder, is within your classifier, you've got the option under Advanced to convert a particular class into annotations. So we could go ahead and convert our tumor into annotations, and then those annotations could then be used within the spatial analysis with respect to the infiltration analysis in particular. So that's a nice way to save time if you do manage to create a successful random forest classifier to identify that tumor. You can convert the mask to annotations to then be used in the infiltration analysis. So go ahead and open up my spatial analysis plot. Sorry, I didn't mean to. Just go ahead and minimize that. And we'll firstly go ahead and select our cells or objects. So maybe you want to take a look at our CD4 positive cells. We then have our tissue annotation layer. So we've got the tumor analysis ROI or the whole tissue. And we'll just focus in on the analysis ROI, which was the teal. If I change this color, then you can now see our ROI has been brought into the spatial plot. And we can then add in our interface layer, which is going to be our tumor annotations. So again, we've now brought those guys onto the plot as well. So lots of colors going on within our plot over here. And what you can also hopefully see is you've kind of got a greeny and yellow markup, which has been overlaid within our region of interest here. And what we can see at the moment is our infiltration analysis before we've optimized our ranges. So you can see we've got a warning that the infiltration bands are too small. So what we're going to do is adjust the ranges here. And hopefully you guys are able to see that the markup is changing. So we've got bands which are inside and outside of our invasive margin, and that's divided up into 10. So we'll be looking at 20 micron increments. If we go for 2, for example, maybe I'll bring these down a little bit further just to make it easier to see. Now we can hopefully more clearly see we've got an internal band in yellow for 50 microns, and then we've got an outside or external region, again 50 microns in the blue. And this is going to be the area which will complete our infiltration analysis within. So we'll be looking for CD4 positive cells which are outside of our tumour boundary, and then CD4 positive cells which are inside that tumour boundary as well. The last one of the points to mention here is you've got the option to include all positive interface layers. Now I find this is easier to explain by swapping from false to true, and what hopefully you saw if we just swap back again is that now we can include our negative annotations as part of our infiltration analysis as well. So rather than having them as exclude, we can have them included as part of the infiltration analysis, which is very useful actually if you do convert your random forest classifier to annotations. You perhaps may have lots of negative or exclusion regions, and these can now be incorporated into that infiltration analysis. We also have the option to store that object or cell data if we wish. We'll leave it as false for now. And then the very last point to mention before we analyse this is we have the option to adjust the band resolution, which is the bands that you can see on the image here. And the only time you would ever need to change this from default is perhaps if we were doing the analysis across a whole slide and our bands were not tracing our tumour margin very well, maybe they were pixelated, then you can increase the resolution here. If we do press high, we'll have a warning or a message here that it's going to say it's taking a longer time to run. So if you don't need that, then please leave it as default. You won't gain anything from changing it to high or highest other than having to wait longer for your analysis to complete. So if you press Analyze, it should be very quick, as being as we're focusing in on a small area. It's taking a surprisingly long time. Okie dokie, so finally complete. So this markup doesn't change. What we've got over here is our CD4 counts. CD4 counts within the interface, so across the yellow and blue bands here. The average distance to the interface is 21.56 microns. If this was negative, it would mean the average was actually within the interface, so inside the boundary that you're interested in taking a look at. Got the average area, the densities, and then the counts. We've also got a histogram here, which is quite simple. We've just got the two bands. So the negative is within the interface, so distance to the interface is minus. So this is our yellow band. And then this one here is outside of the interface, which is our blue band. So you can see we've got an accumulation of our CD4 positive cells outside of the tumour. Again, we can save this or take a snapshot if we wished. So the last thing we're going to do is just go ahead and save some of these analysis settings. so we can run them in batch mode. So I've just pulled back up my plot and opened up the nearest neighbour analysis plot, popped in 2 different cell types of interest. And to save these, if you come down to setting actions, you can come to save here. You can also export if you wish. So we can call this batch nearest neighbour test. And they'll be saved to the study where our images are. Once they're saved, we can close down this box, and you can also close down the plot as well. You don't need to save that unless you wish. So if we come back to the Studies tab, this is where we launch all of our batch analyses from, whether that be classifier, regular analysis, or spatial analysis. And when you do want to do batch spatial analysis, if you come to this tab here, select the images that you're interested in performing the spatial analysis on, right-click and come down to results here. So normally we would go to analyze. You want to come down to results instead. And now you can see all of the results which are associated with these 2 images. Now, one of the important things to remember is we want object data. So you're able to filter these here. So if you do just want to bring up all of the results which have object data set to true to maybe help tidy up this table, then you can do so. And then you can also go ahead and select the results that you might like to do batch spatial analysis with. Come to result actions, and then you've got the option to plot if you wanted to do batch spatial plotting. But if you're not wanting to generate one of those plots, then you can actually go straight to spatial analysis. And you'll see here we've got spatial analysis settings which have been generated and saved previously. So these are the ones which we just created. So we can select them over here, and you'll see we're creating job 1 of 2. That will then go to 2 of 2. And hopefully we'll be able to see over in this analysis column here some queued and completed messages. So batch job creation is completed. So you see you've got a queued message here. We can close that now and refresh this, and we'll eventually see when it's completed. So one thing to note with batch spatial analysis is that obviously we've set our filters based on phenotypes. So it's very important for your phenotypes to have identical names. That even comes down to capital letters and spacing. So we'll see both of these images. When we open them, they've got identical phenotypes which have been specified. And that is key to being able to run batch spatial analysis successfully. Make sure you have your phenotypes labeled identically. So perhaps you might need to optimize your nuclear detection settings or set very different, slightly different thresholds, maybe on a couple of images. That's fine. You can run different analysis settings on these images as long as the phenotypes or the filters that you apply are identical. So you can see here we've successfully ran a batch nearest neighbour test. We've got our simple results here, and again for this image we've also got our simple results here as well. So that wraps up our spatial analysis portion. Very shortly I'll show you how to export all of the data associated with your images, but I'll just go ahead and pause and see if we have any questions.
Hi, is this spatial analysis only a part of the HyPlex module, or is it available in the other one too?
You can use spatial analysis with any module which creates the cell or object data. So as long as this table is populated, then you can go ahead and do spatial analysis.
Thank you.
Okay, so we'll go ahead and look at exporting now. So again, we can also export in batch mode, and all batch type of analysis exporting is done from the Studies tab again. So if you have images which you'd like to export from, again, you can select those, right click, and come to export here. So you've got the option to export summary data, object data, annotation measurements if you wish, but what we'll take a look at is advanced here. And you can see now our export manager has popped up. So we've got the option to really export everything associated with these two images, whether that be markups, the results, or any of the settings. And this is all done via the export manager. So you've got the option here to export thumbnail-sized, mid-sized, or full-sized images. Just for an example, if we press full-sized, you'll see the total size to export is almost 12 gigabytes just for two images. So I would recommend going for the mid-sized option. Obviously, if you're then maybe doing one publication standard options, then you can maybe look at exporting full-sized. But that's obviously going to take up a lot more space, so it's just something to be very aware of. You can export everything associated with that image, so you can export input images if you wish. Maybe I'm not really keen on that option. We can then export the analysis markup, so that would be the cell-based markups there. The classifier markup, which we do have some of those. It also gives you the option to specify that transparency, any plots which are associated with the images, so maybe histograms or any saved spatial plots. And then over here on the right hand side, we can export that summary data, so that was the top table in the results column. We can export object data, so that was the bottom table in the results tab. And we have the option to split the job. So if you are exporting data for multiple images that all have object data, if you want each of those object data files to be generated into a separate spreadsheet, then make sure you tick split job, else that will all be combined into one very large spreadsheet. Then have the option to export an analysis report, which is it's going to be a Word document, so it'll give us some thumbnails and that summary results, as well as the algorithm which is used. Quite a nice way to do things. And then if you have registered images, then you can also export the XY coordinates for those registered images all within the data. We have some others. So any annotations you can export. You can also export those analysis settings and classifiers if you wish. And then you can choose the file, the folder where you'd like those to go. So you can see we've got several sets of results here which we can choose to export. So you can export all of these, the first, the second, etc. Or you can select from the list. You can just hold down the control key and highlight the ones that you'd like to export. So if we just do a selection, for example, press generate, export selected only. So we're just focusing in on the images or the results that we would like to export. And then once the export is complete, we'll have a File Explorer window which pops up, and we can take a look at the export in a little bit more detail. So we've got our archive folder here. Any classifiers we'd exported would be there. We've got lots of different images here. So we've also got the annotation files and the analysis settings. So lots of images there, and they're all the mid-sized, which is what we selected. If we had any plots, they would be in this folder. We've then got the analysis report, which is going to be that Word document. So you've got those thumbnails the settings and the algorithm that was used. And then we've also got some summary results. Just taking a second to open. Oh no, this is the object results, sorry. So this will have all of the object or cell data, which will be a lot of information. So we've got data for every individual cell here with all of those headings. So our DAPI, FITSI, etc. all contained there. And then the summary results as well. So we've got the summary results for each of those images all contained within that one spreadsheet. So the next thing we'll look at is registration. But again, I'll just pause to see if we have any questions. Okay, so we'll go ahead and move on then. So what we have here is 3 images or 3 serial sections that have been stained for different markers. So we've got a CD8 stain on this image, a PAN-CK on this image, and then we've also got a CD4 stain on this image as well. And the first thing we're going to take a look at is how we would register these images together. Actually, the first thing we're going to do is just get rid of the annotations. Just so when I redraw them to check how well registrations worked, it'll be nice and clear. So you have different options with regards to registration. You can either select the images, right click and go to register, or you can come to Tools, Image Registration, New Registration, and then you've got the option to register the images here. Going to the Tools and selecting Image Registration here means we can only we have to wait for this registration to complete before we can queue up the next one. Whereas if we select the images, right click and go to register, this is essentially our batch registration, which you can see up here. So we can load up stacks and stacks of images to be registered. And I also personally like this because you can see the label as well, so you can check what the stain is, which you need to fill in. Whereas the option from Tools and Register, you just got the image path, which for my images it's fine, they've been labeled correctly, but if you kind of have a generic name, maybe just numbers, for example, whereas you want to identify the stain, doing the option via batch registration just gives you the availability to look at that label for a bit more insight. So this is what we'll go with now, and the first step is to type in the stain. So I've already registered and unregistered these, so Halo's remembered the stain name here, which is handy, but that's very important that you do name these correctly, at least so you can distinguish between them for reasons which will become clear very shortly. So we do have options under settings to use default or serial stain registration. I would always recommend going with default registration first, as that typically works very well in most cases. You can then, if maybe it doesn't, take a look at the serial registration, where you have more options. Perhaps you want to focus in on that high resolution registration to try and improve your registration without doing any manual changes. We'll just go with default for now and press register. They've skipped the queue and gone straight into being analysed. And what we could do now is select more images, right click and press register, or drag these over here, press register, and then they go into the queue, and we can kind of build up that queue so we can have batches of images go ahead and be registered. What we can see over here is the percentage completeness. So we're just waiting for that to get to 100. So our registration is now complete, and you'll be able to see we've got this little icon here, which means our images have been registered. We have different viewing options in Halo, so if you right click on an image and press Tile all tabs when you've got multiple images opened, you'll be able to view these guys all next to each other. And if you come up to Tools and Image Registration and press Synchronize Navigation, you see we've got a hand on the CD8 image, so the left-hand side image, and then we've got a black circle on the other image. And you can zoom in, maybe kind of trace the edge of the tissue, see how well things have lined up. Or what I like to do is grab the flood fill and do a quick flood fill annotation on my on one image and see how well that's overlaid onto the corresponding images. And you can see hopefully that registration has actually worked really quite nicely. If your registration wasn't quite so successful, you do have the option to do some manual adjustments, and that's under Tools, Image Registration and Landmarks. So I'll just save those annotations. And maybe, so we've got 3 images open, so it might be slightly harder to see, but you've got a pin icon here now in all of your images. And what you can do is, hopefully you can see over on the left hand side, I've got my cross. So we could just go ahead and drop in this pinpoint here, select the hand and move this landmark to the correct position on the other images. We could then apply this and that way we could manually improve registration if it wasn't quite up to scratch. So you can press OK and apply. I'm not going to do that as my registration has worked very nicely for these images, but it is an option that you have if needed. So now our images are registered. In fact, I'll close one of them down just for now. One option we do have is perhaps we would like to apply a classifier which has been made based on our pan-CK tumour staining. So we can create a classifier on this image to segment tumour and stroma perhaps, and then those regions which have been classified can actually be applied within analysis settings which are ran on a corresponding registered serial stain image. So for instance, we could look at CD8 positivity within tumour and stroma compartments based on a classifier which had been made using the pan-CK image. So if this is something we would like to do, the first step would be to create that classifier, which I've already done ahead of time. So we've got our tumour, stroma and glass. So if we go ahead and pop on our real-time tuning window, you'll see we're pulling up the tumour in red, the stroma in blue, and then our glass areas are in this greyish colour. So that classifier has been made and saved, and that's based off of our pan-CK staining. If we move into the Analysis tab here, maybe load up some area quant. That's nice and simple to optimize. Choose our stains. Just check. And deconvolution. Looks good. I'll choose our CD8 markup. That looks okay to me. So we'll leave the settings as they are. We've already gone through how to optimize area quantification. But the one thing we will look at is the advanced settings here and how we would apply that classifier from the registered image. So the first thing we need to do is go ahead and, select the classifier. So this is the same as before. We click on the box here, click on the classifier and select this, and we can then choose our class list. So maybe we're just interested in tumour and stroma. And we could simply run the analysis now, but the classifier obviously wouldn't work very well on this image as it's been optimized for our pan-CK staining. So what we need to do is come down to classifier registered, and you'll see you have two options here. So we can either choose to base it off of the CD4 image or the pan-CK, as our image is registered to both of these. So you just need to make sure you select the appropriate image, which is why the name that you give to the image is very important. If we just called them 1, 2, and 3, for example, it would be very difficult with my memory, especially to remember which image referred to which number. So we'll go ahead and select the pan-CK. And then if we zoom out on this image, and if we just choose to analyze that annotation layer, this should take a second or two for the class to begin. So once the classifier is ran, the analysis itself will be relatively. Maybe the image is bigger than I thought. So classifier is just finishing, and then the analysis should just whiz through. Whilst it's going, just as a reminder, if you do run this local analysis, the green squares have been analysed to their tiles which have their analysis completed. The yellow ones are the ones which are currently being analysed. Orange, if you see those, it's just going back to confirm, and then the white tiles have yet to be analysed. But we're very nearly there. Great, so our analysis is completed. So we've got the markup looking at our CD8 stain, just for area quantification. And if we hop across to our results tab here, you'll see we've got the results for our classifier. So tumour, stroma, glass. We've got the overall results, so that's for the tumour and stroma and glass areas combined. All the typical results we get with area quantification, so that the weak, moderate and strong classification, which is reflected by the yellow, orange and red in the markup here. And then we've got those results broken down into the tumour compartment and then the stroma compartment as well. And if we toggle between that classifier markup, if I close this image down so we can see it a bit more clearly, you'll see we've got the classifier which has been applied from our pan-cytokeratin image to our CD8 image. So we're able to quantify that CD8 staining within our tumour and stroma compartments based on the pan-cytokeratin serial stained image. So that's one way that registration works. The other option, which is all kind of combined within the registration module package, is the option to fuse serial stained images, and we call this the serial section workflow or the serial stain workflow, but it kind of comes under the umbrella term of registration module. So that's what we're going to do now. I'll pause again very briefly to see if we have any questions, as this is the last topic to cover for this session. Okay, so we'll go ahead and get cracking then. So the very first thing we're going to do, so we'll just fuse two of these for ease. We open up the images here. Is if we come to Analysis, Setting Actions and Load, we'll load up our deconvolution settings. And you'll see we've got the option to deconvolute up to 5 stains. So the workflow, what we need to do firstly is to convert our bright field images into pseudofluorescent images, and that's done using the deconvolution module. And then once we have those pseudofluorescent decon files, we will register those together. And then once that registration is complete, we can then fuse those into one multi-channel pseudofluorescent image. And then using that new fluorescent image, we could then go ahead and analyze it using Hyplex or any of the fluorescent modules, just as you would a typical fluorescent image, so that there'll be no difference there. So you can make a nice multiplexed image from your serial sections. So the first thing we'll do is go ahead and select our stains off of the image. We'll give it a name actually first. So do hematoxylin and PanCK. So go ahead and select a stain off the image for both of these. And if we pop on our real-time tuning window, firstly we'll just be looking at the deconvoluted image for hematoxylin, and then we can look at the deconvoluted image for the PanCK. Now sometimes, even though we only have 2 stains here, it can be helpful to add in a third stain for background. That can sometimes help to improve the deconvolution. So we can go ahead and add it for now and see if it helps. So maybe we'll leave it on for this example and we'll see how we go. So if we had a whole batch of images we would like to deconvolute using these settings, we could save them and launch that deconvolution in batch mode, which I'll show you how to do. So we'll just save them for now then. Press OK. I'll just analyze the entire image firstly and select the folder. So we need it to go into the same folder where the original images are. Press OK, and then we've got that image available there as a pseudofluorescent with our different channels, which we can toggle off and on. And we'll now just do the same for our CD8 image. We could go ahead and reselect, or we can take a look and see how well these options are working for us. So that looks to be working pretty well. So again, we'll analyze that entire image, select the same study where the original S3S image is located, and we can also toggle it to almost a pseudo bright field image in order to take a look at how well that deconvolution's worked if we wish. So we've got our 2 images here. We've got our PanCK image, which we can toggle that background off. So we've just got our PanCK staining and hematoxylin visible, and then we've got our hematoxylin and our CD8. One thing we can do is we can go ahead and change these colours. So if you want to put them back to colours which maybe match, that's probably the wrong one, match maybe what you saw initially with the hematoxylin in blue, and then your CD8 in a brownish colour, then you can actually go ahead and do that if you wish. If we hop back to the Studies tab now, we're in the Pancreas panel folder, and you'll see we've got two new images. So we've got our DCON PanCK and then our DCON CD8 image. If, for example, we wanted to batch deconvolute multiple images in the study, if we select these and go to deconvolve images, we've got the settings that we'd save. You just press deconvolve, it only takes a second or two, and then they would be generated and available in that folder as well. So the next step in the workflow is to register our two deconvoluted images. So we can right click, go to register. So we've got CD8 and PanCK. I just right clicked and pressed remove stain. So if I press register, these images have gone straight to analysing, and hopefully that should only take a minute. So that has now completed, and we've got our two registration icons. So if we tile these tabs, come to view, tools, image registration and synchronized navigation. So it's yellow now, so it might be a little bit more difficult to see because these are fluorescent. But we've got the hand, got our small yellow dot. So if I move it onto a patch of blue, hopefully you can see that now. And again, I just recommend using that flood fill annotator to grab the whole tissue, and you can check how well that didn't work very well. Check how well that registration has worked between the two images, which you can see it's actually worked really quite nicely again with those DCON files. So once you're happy with the registration, and again this is really the best way to check, I find, during this annotation, either a whole flood fill or just using the pen tool itself. The next step is to select those images, and now what we're going to do is fuse them into one. So if we right click and come down to fuse, you see you've got the option to fuse channels, which you can use to fuse single channel images into one multi-channel image, depending how they're brought into Halo. But what we want is the fuse serial stain option. So we select this, and you'll see now we've got our two DCON files here. So the pancreatic CD8 DCON and then the pancreatic PanCK DCON. And by default, all channels will be combined into the new fused image. But if you're just wanting maybe your CD8 stain to be brought on to your PanCK image and you're not interested in having two hematoxylin channels, what you're able to do is duplicate a particular image, and you can just go ahead and select the channel of interest. So we didn't actually need to duplicate for this, perhaps. Maybe we'll just choose the PanCK stain to be brought onto the CD8 image, but you can really just go ahead and specify what stains you'd like to be incorporated onto what images, and by duplicating or just selecting a single stain, you can actually then go ahead and rename each channel here. So you can, rather than having CD8 hematoxylin, CD8, PanCK, which has been brought in from the registration, you can just go ahead and specify those as you wish, and also change the colours as well. So the next thing to mention is your output file type. So you've got the option here to do TIFF or serial. Now my very first recommendation is to always select serial. Now this file type will be generated almost instantaneously. So if we just go ahead and press fuse for now. Just name the file, and it does need to be stored where the original images are. So the image is just being loaded. Hopefully it will be with us very shortly. But you can see over here in the left-hand panel, we've got the CD8 panck.serial image. So close those up so we've got more space. And what we can see here now is we've got the pseudofluorescent fused image with the hematoxylin, the CD8 and the pan-CK, and it's a .serial file generated almost instantaneously. But what that means is the fusion is generated almost on demand. So we zoom in to this region and it will kind of be fused as we zoom. If we move up to a different image, it'll again just take a second or two whilst the fusion occurs. And the serial image is really for you to check that you're 100% happy with registration before you go ahead and create the .tiff file, as the .tiff file will generally take quite a few minutes to generate as Halo's writing a whole new image. So the serial image isn't for you to analyze, so we wouldn't go into the Hyplex module now and perform analysis on the .serial image. That can cause problems with how long it actually takes to process and things. It's simply to check the registration, and I can't reinforce that enough. Sometimes we've had difficulty in the past with people wanting to maybe reduce a bit of time they're waiting for the TIFF image to be generated, but we really don't recommend analysing this .serial image. Check your registration, make sure you're happy, and then you can go ahead and fuse into that .tiff image. But just as a reminder, you can toggle any of these off and on as you would with a normal fluorescent image. Really zoom in and make sure you're fully happy before you want to generate that TIFF file. If you do want to generate the TIFF file now, so you're happy with registration, you don't think any improvements need to be made between these two, again, it would just be the same steps. So you would have to duplicate these. Select your channel of interest, change the colors again if you want to. You can change them once the image has been fused, that's fine. And then you have the option now to generate that TIFF file. Again, when you press fuse, you just be asked to save this. And again, it needs to be where your other images are located, so where the DCOM files are located, all within the same folder. So we can call this the same name. I just call this one. I'll press save, and so that will go ahead and fuse into a TIFF file that we could then go ahead and perform Hyplex analysis on. So you can see it probably only take maybe 2 minutes or so. But then once that is generated, you can use it as you would a normal image with any fluorescent module and just be analysed as normal. So that concludes really everything we were going to cover today. I'll go ahead and press stop recording